Hello! So welcome to part 2 of Kinetics, and we're going over the rate law in this video. Kinetics is pretty much what you're going to get hit with first at the beginning of your Chemistry 2 semester. So right now in this video we're going to go over the rate law. Last video, if you haven't seen it, go back and familiarize yourself with the reaction orders in part 1 of this series. So the reaction order, and I want to remind you that order I have in quotations because it does not mean chronological order. It does not mean the order in which you solve a problem. It does not mean any chronological order that you're going to perform any tasks or anything. The word order in this case is just used to describe the different categories of rate and how the rate depends on the concentration of the reactant. So say we have a molecule A here, and then the yield arrow, and molecule A turns into products on the right side of that yield arrow. So the reactant is going to be the A. It's going to be, the reactants are anything on the left side of the yield arrow. So those are the ingredients, if you will, that you put into to get a reaction, and then the products are what you get out of it. The products are what you produce from these ingredients, the reactants. So if you have the reactant molecule A and it turns into products, the rate, the initial rate, and that means how long it takes before the reaction starts. So if you take like baking soda and vinegar, if you remember making a volcano when you were a kid in a science class, if you take some baking soda and vinegar and put them together, then almost immediately you get this big foam. It turns into this big foam. So that is almost an instantaneous reaction when you put the vinegar and baking soda together. But once we get down into the details of chemical reactions, there are differences between how long it takes for the reactions to start happening when you mix all the chemical ingredients together. So this is what we're looking at. We're looking at how the initial rate is how long it takes before the chemical reaction starts to happen. And the initial rate depends on the concentration of the reactant. So that would be A in this case. And we're going to put little brackets around the A to denote that we're talking about the concentration. And of course the concentration is pretty much used interchangeably with molarity. And molarity is the number of moles in a liter of solution. So if you don't remember what molarity is, go back to your Chemistry 1 class notes and refamiliarize yourself with molarity. So there are three basic orders that you need to worry about for Chem 2. Now it does get more complicated than this if you go further on into more advanced chemistry classes, but for Chem 2 you need to know these three basic orders. And the first one is the zero order, and the zero order is when the rate is independent from the concentration. The rate is not affected by the concentration. of the reactant A. In this case, we're talking about A. I'm just using A as a general reactant. And then we have the first order, where the rate is proportional to the concentration of the reactant A. So if you have a concentration of 2 molarity of A, the rate could take 2 seconds to start before it starts reacting. But if you have 4 molarity of A, the rate could take 4 seconds to start. So see, if you increase the concentration, then you increase the amount of time it takes before the reaction begins. Now the second order is kind of like the first order. The rate is affected by the concentration of the reactant, and it's also proportional, but it's proportional to the square of the concentration. And I'll show you on this next page an example of this. So here's some examples of the reaction orders, just to refresh your memory. In 0 order, remember the rate is independent from the concentration. So let's look down here at this little chart. Here's the concentration of A, and notice I have it in brackets, and that means concentration. And then down here I have in parentheses the capital M for molarity, just to remind you that we're talking about the molarity of A, which is the concentration. And these are 3 different experiments. 1 experiment, 2 experiments, 3 experiments. The first experiment, our concentration of A was 0.10 molarity. Our second experiment, our concentration, we doubled that to 0.20 molarity of A. And our third experiment, we doubled that concentration and to 0.40 molarity of A. But notice that the initial rate, and this is rate with a little lowercase I next to it, just to show you that we're talking about the initial rate being when it starts, when the reaction starts. So look at, we timed when the reaction starts after we put these different concentrations of A in as ingredients, and look, these are all the same. They did not change. So that is why this, in the 0 order, the rate is independent, doesn't change depending on the concentration of the reactant A. So this would be written as, we would put the concentration of A here with a little bracket on it to show concentration, and since it's 0 order, we would put a 0 up here as a little exponent. Now let's move on to the first order. The first order here, and look at this chart down here. The first order, here's another set of experiments. Experiment 1, Experiment 2, Experiment 3. And between Experiment 1 and Experiment 2, we doubled this concentration. See how in Experiment 1, our concentration was 0.10 molarity. And in Experiment 2, our concentration was 0.20 molarity. So that means it's times 2. So we doubled it. And also, if you look from Experiment 2 to Experiment 3, we went from 0.20 molarity to 0.40 molarity. So that's also been doubled, so times 2. So now let's look at what changes this brought about in the initial rate. The first experiment with the concentration of 0.1 gave us an initial reaction of 0.015 seconds. And then the second experiment with the concentration of A being 0.20 molarity, the initial rate also doubled. Look at that. It went from 0.015 to 0.030. So that also doubled. And then let's look between experiments 2 and 3. We doubled the concentration again. We went from 0.20 molarity to 0.40 molarity. And look at the initial rate. We went from 0.030 to 0.060. So that also doubled. So when we doubled the concentration, we also doubled the initial rate. So that's called first order. And again, if you're not familiar with this, if this sounds unfamiliar to you, go back to my part 1 video of this and I break it down for you even more. But so just to refresh your memory, for first order, we put the A in the brackets showing concentration, and then the little exponent up here is going to be 1 for first order, because every time we doubled the concentration, it also doubled the initial rate. So these both increase, the concentration affects the rate, and they both increase at the same pace. Now second order is kind of like first order because the initial rate increases as we increase the concentration. But look at this, we went from 0.10 to 0.20, so that's a doubling. We doubled this. And we went from 0.20 to 0.40, so that's a doubling. We doubled the concentration again. But look at the initial rate. The very first initial rate for 0.10 is 0.015. And as we doubled that concentration in the second experiment, this shot up to 0.060. So this did not double when we doubled the concentration. This quadrupled. It went up 4 times, not 2 times. And let's look at experiment 2 and 3. On the concentration side with the A, the concentration side we doubled. We went from 0.20 to 0.40, and that's doubling times 2. But the initial rate went from 0.060 all the way up to 0.240. So again, that's quadrupling. And so in second order, we're going to write this with the concentration of A and a 2 as the exponent. And that denotes that this concentration of A in this specific experiment is in the second order. Now let's go into the rate law. Now that we've gotten a handle on the reaction orders of things, at least the 0 order, 1 order, and 2 order, we need to talk about the rate law. Now, if you're taking, let's use A again. We're going to take A as our chemical or our molecule, and then that yield arrow, it's going to yield products. So as long as this rate law is in effect, as long as the reverse, so the reverse would be you take the products and you turn them back into A. As long as the reverse reaction is slow, is very, very slow, then we can use this rate law. Now the rate law is describing the relationship between the rate of the reaction and the concentration of the reactant. And remember, the A is the reactant, the ingredients that you put into in order to react to make a product. The ingredients you use is the reactant. So right now we're just using one ingredient, A, for simplicity. But the rate law is the relationship between the rate of the reaction, and that's how fast the reaction happens, the rate, how fast the reaction happens, between the rate of the reaction and the concentration, and remember the concentration is going to be designated by putting the A in brackets. And this is going to be the same thing as saying molarity, the molarity of A. The relationship between the rate of the reaction and the concentration of the reactant. Well, I always think of chemistry as cooking out of a cookbook and using a recipe to cook. So I'm going to put, for the reaction, I'm going to put down in parentheses the ingredients, because the ingredients are what the reactants are. The product would be like the cake you make, but the ingredients would be the flour, the sugar, and the eggs. And so the ingredients, that's what we're talking about when we talk about reactants. Now, the rate law itself is the rate of the reaction. And again, think of that volcano when you put the baking soda and the vinegar together and it makes the foam. That's a chemical reaction. So the rate, how long that takes, the rate of the reaction is going to be equal to K, and this is this little lowercase italicized K. So I'll put lowercase, and it's usually in italics. K times the concentration, and the concentration is designated by these little brackets. And that means molarity, so that's capital M. And then this little n exponent up here, and that is whatever order this is in, if it's in 0 order, 1st order, or 2nd order. So the n stands for the order. So I have this guide down here that explains this. So the n is the order number. So if you're in the 0 order, it would be 0. If you're in the 1st order, it would be 1. If you're in the 2nd order, it would be squared. You'd have a little 2 up there. The K is the rate constant. Because it's a constant, it doesn't change, but it's not the same number every single time you do the formula, because the constant in this case is different for each reactant. So A might have, a certain amount of K. It could be 0, 1, 2, 3. But if we're dealing with oxygen, K might equal 1.827. So it depends on the reactant that we're talking about, what the K is. And so you have to find out what the K is depending on all of the other information you get in the equation. So here's some more, this is a little bit more into detail about the rate law. And I wrote, just so you can remember up here, the rate equals that K constant times the concentration of A to the power of the order of, this is an N, so that just means whatever order you're in. So first, let's look at 0 order. Oops, let's change. Let's look at 0 order. And so the rate law, rate would be right here, would be the K constant times the concentration of A with the 0 exponent. And we have the 0 exponent because it's the 0 order. If you don't know how to determine what order, which order the reactants are in, go back and watch my part 1 video, because I break it down a lot easier in a lot more detail, and it's only about 20 minutes long. Here's the order is 0, so therefore we're going to put a 0 exponent here after the concentration of A. Now, if you know anything about math, you know that anything to the power of 0 is going to equal 1. If we have 32 to the power of 0, that's going to equal 1. It doesn't matter what this number is. If it's to the power of 0, it always equals 1. So in the 0 order, the reactant, A in this case, is to the power of 0. So that means that A, the concentration of A, equals 1. So when we plug this 1 back into the formula, this K times the concentration of A to the power of 0, all we're doing is we're saying K times 1, because A to the power of 0 is 1. So K times 1 is what? Just K. So remember, in 0 order, the concentration of the reactant does not affect the time it takes for the reaction to happen. That's why the concentration of A in this 0 order formula gets nixed out, and we just end up with a rate of K all by itself. Now for first order, the rate formula would be K times the concentration of A, and since it's first order, the exponent here is going to be 1. And since A, the concentration of A raised to the 1 power is just plain old concentration of A. So we don't have to really put that 1 there, it's implied. So your rate law for the first order is just K times the concentration of A right here. Now for the second order, again it's K times the concentration of A, but since we're in the second order, we're going to have a 2 as the exponent up here. It's going to be squared. So A squared, or the concentration of A squared, is going to be the concentration of A times the concentration of A. So the rate law for the second order is really going to be K times the concentration of A times the concentration of A. Or if you want to write it shorthand, it would just be K times the concentration of A squared. Now that we've figured out K is, or the rate is K times the concentration of A to the 0 power, which just means K, because the concentration of A to the 0 power is just 1. So the initial rate, and here's this little, this is a lowercase italic I as a subscript I put on there, just to show you we're talking about the initial rate. And the initial rate is when the reaction starts. So the initial rate is going to equal K, the rate constant. Now in the first order, now that's, I say that, why did I say that? That looks like kind of obvious, but I'm just saying that to set up the format, because when you get into the first and second order, it gets just a little tiny bit more involved. So I wanted to start us with the basics. So the 0 order, the initial rate is just K. Now in the first order, we have K times the concentration of A to the first power, which is just the same thing as the initial rate equals K times the concentration of A. Because remember, we don't have to put that 1 up there next to the concentration of A, because 1 is implied. So it's just K times the concentration of A. So if you rewrite this, if we have the rate, the initial rate equals K times the concentration of A, but we want to find out what K is, then we can divide the concentration of A on both sides to get K alone, and we end up with the initial rate divided by the concentration of A equals K. So that's if you want to solve for K. you want to get everything else on the other side of the equal sign and just get K isolated by itself. So we can solve everything over here, the initial rate and the concentration of A, and then that'll give us the answer K that we're looking for. And these are just algebraic rearrangements. I'm just rearranging the formula. I'm not giving you any new information. I'm just rearranging the formula so you can see that you can just rearrange the formula around in case you're solving for K. You might not be solving for the rate. You might be solving for K, or you might be solving for the concentration of A. So this is just how to algebraically rearrange these formulas around so you can use them. Now the second order is K times the concentration of A squared, which is the same thing as the initial rate being equal to K times the concentration of A times the concentration of A, because the concentration of A times the concentration of A is the concentration of A squared, right? So if you want to isolate, if you're solving for K, you don't know what the rate constant is for this formula. You want to solve for K, then you want to keep K on this side of the equal sign and get everything else over on the other side of the equal sign. You want to isolate the K. So that's how we can do this down here. We just took the A concentration of A squared and we divided it. And so the initial rate divided by the concentration of A squared is going to equal your K. So again, this is not new information. I'm just taking the exact same formula that we have up here, rate equals K times the concentration of AN, and I'm just algebraically rearranging the letters on here so you can see that we can rearrange this and solve for different things. Now, this is from our first video, part 1, and this is just a little friendly reminder. The rate itself, just any old plain old rate, is the change in the amount, which is the final minus the initial. You want to start with the final, and then you want to subtract the initial. And change is denoted by this triangle, which is called delta, and that just means change. That's just final minus initial. So the change in the amount of something over the change in the time of something. And this is just plain old rate. This doesn't even have to do with chemistry. This is just rate in general. So if you start at your house, and you get in your car, so you set the odometer and you start at 0 miles and you drive 60 miles. So your final is going to be 60 miles. So we're going to put that first. 60 miles minus 0 miles, because you started at 0 miles, you started at your house. That means you would have the change in the amount of miles you drove would be 60 miles. And then over that, if you left at 2 p.m., that's the initial, so that goes at the end, and you got there at 3 p.m., that's the final, so we're going to put that in the front. 3 p.m. minus 2 p.m. equals 1 hour. So that means you drove 60 miles per hour. So that's the speed, which is a form of rate. That's the rate at which you drove. So that's just a general concept of rate. But it's exactly the same in chemistry. We're just specifically talking about the reaction of the chemicals, the rate of the reaction of the chemicals. But the rate, it's still the rate. It's still the speed at which something happens over time. And in this reaction rate, it's going to be the change in the concentration. So that would be that brackets A that I was showing you, which is molarity, which is the concentration is usually in molarity. So you start with the final amount of the concentration, and you subtract the initial amount of the concentration you started with. And then you time it from the time that you put all the ingredients in until the reaction takes place. So the reaction takes place at the final, and the initial is when you start. So if you start at 0 seconds and it took 1 second before the reaction took place, you go 1 second minus 0 seconds, and that's 1 second. So here's this triangle again. The triangle just means change. So the change of the concentration of A, which is the reactant, the ingredients, over the change of the time. So the T is time, the lowercase t is time. So I'm refreshing your memory on that because that's going to come in handy here in a second. So the rate law is this one on the right that I was telling you about. The rate equals K, the rate constant, times the concentration of A, all to the power of whatever order the formula is, 0, 1, or 2. But also, what did I just say about the rate? The rate is also just the change in the concentration of A over the change in the time. Because if you start out with 10 moles per liter of A and you make products with some of it, and you're left with 5 moles per liter of A because the other 5 got used up as to make the products. So the other 5 got used up making the products. So the change in the concentration in this case would be your 5 moles, your final measurement, 5 moles per liter of A, minus your initial measurement, which is 10 moles per liter of A, and that would be negative 5 moles per liter. Or that's the same thing as saying negative 5 molarity. So as you notice, these reactants, when you take A and you make products with it, you're going to lose some of your A. So your change in your concentration is going to end up being a negative number usually. So just keep that in the back of your mind, so in case you run into negative numbers, don't freak out. It's supposed to be like that because reactants get used up to make the products. So you're going to end up having a negative number in the change in concentration. Now, since we have this rate law, rate equals K times the concentration of A to the n power, but also just a general rate is always going to be the change in concentration over the change in time. We can do this. We can do this fun math thing. So the rate is going to equal the rate. The rate's the same, is going to be the same thing. So if we take the change in the concentration of A over the change in T for time equals, and this would be equaling the rate. This equals the rate, right? Well, instead of writing rate right here, we can take this other definition. Let me get a different color. We can take this other definition of rate and we can substitute that into the word rate. So instead of writing the word rate, we can put in K to the times the concentration of A to the order number, to the power of the order number. So the change in the concentration of A over the change in time is going to be equal to the rate constant times the concentration of A to the power of the order number. And this is what is called the differential rate law, what I just did, the differential rate law. So here it is again, the rate is the change in concentration of A over the change in time. And over here also the rate is the rate constant, K, times the concentration of A to the nth power, and the n is the order number that this formula is in. So we can replace the word rate in these formulas, and we end up getting this entire formula right here. And that's called the differential rate law. So here would be zero order. Change this. Here would be zero order, and remember the initial rate is going to be K because A to the power of 0 is just 1, so we're just going to have K. And the generic rate rule is the change in the concentration of A over the change in time, and so that's going to be equal to K right there. Now in the first order, we have the rate, the initial rate, is going to be equal to K times the concentration of A. Here's our general rate law, the change in the concentration of A over the change in time. And so we can just bring this right down here and have that equal the rate constant times the concentration of A. I hope you're following this. And if you're not following, if you're still kind of hazy about these orders that I'm talking about, go back and watch the first video first. It's like 20-something minutes, but it breaks it down totally so you're solid on what you need to know for the next video. Now the second order is going to be K times the concentration of A squared, or the concentration of A times concentration of A. It's the same thing. Concentration of A squared is the same thing as concentration of A times concentration of A. So here's our general rate law, and we can just bring this down here and have, for second order, have the concentration, the change in the concentration of A over the change in time equals the rate constant, which is K, times the concentration of A squared. That's for the second order. And this will all get put together, and you'll see how to use all these formulas in the next video. But it's just a lot easier to learn if first, I know it sounds backwards, but if I show you these formulas first and then I show you how to use them, it'll be a lot easier to understand. Now here we are back at zero order, and we know from that integrated rate law that the change in the concentration of A over the change in time equals K. And then I just skip this step because you don't need to know the calculus for this for chemistry 2. So I'm just going to go, because calculus, we can rearrange this formula into this one down here. So the concentration of A at T, which is time, which is the final time, remember final minus initial, equals negative K times time plus the concentration of A, and this O is for original. That's not the same thing as zero order. Zero order, it would be written up here. So that's The O down here at the bottom, this is an O, not a 0. And this is just to designate that it's the original time, the time you started at. So if you started at 0 seconds, if you're using a stopwatch and you started at 0 seconds, then it's 0. But the concentration of A, whatever the concentration of A was at 0 seconds is what goes right here. Now the first order, from our previous slide, we learned that with this integrated rate law, the change in the concentration of A over the change in time equals the K constant times the concentration of A, because we don't need that 1 there because the 1's implied. So because calculus, we can rearrange that formula into this one. And this ln that you're seeing, ln is like the opposite of log. It's the natural log. It's not the opposite of log, but it has to do with logarithms. And this is something you need to find on your calculator. Find the ln button on your calculator. It's usually right next to your log function on the calculator. And you just punch in the button that says ln, and it gives you a parentheses, and then you just punch in whatever the number is of the concentration of A at when it gets done at your time, when you stop your stopwatch, the concentration you end up with. So that's what ln is. And you can also watch on my Chemistry 1 videos. I have a series about logs and natural logs and base 10s and where that all comes from if you're interested or if you want to know more about it. But really, you just need to know to punch in ln on your calculator, and then you punch in the concentration number. And same with this, ln. And this is A with that O in it. That's the original concentration that you started with. So in my previous example, I said we started with 10 moles per liter of A to make products. And we ended up with 5 moles per liter of A because 5 of the moles got used up in the products. 5 went to product heaven. So we ended up with, that's your final is your 5, and your initial or your original would be 10. So in this case, in the first order, your A concentration O would be the 10, and your A concentration of T would be the 5. And notice here, remember when I was telling you that you're going to have a negative number a lot of times when you're dealing with reactants, and that this formula takes that into account. It has this negative K times time in it. And you'll see why we're rearranging these formulas in this format in a second, because this is the format you really want to be able to work with. Okay, so second order, we know from the integrated rate law that the change in concentration of A over the change in time equals the K constant times the concentration of A squared. And then because calculus, we can rearrange this into this formula, and that's 1 over the concentration of A at the end. This T is for time. This is like when you stop your stopwatch and you take the time. So this is your final concentration, and this is your original concentration. That's why I put an O at the end of it. So it's 1 over your final concentration of A equals your rate constant times time plus 1 over your original concentration of A. And if you're not understanding what to do with this information, it's totally okay. We're going to do that next. I'm going to show you why this is important to be able to rearrange these formulas into these calculus formulas on the bottom. And you don't need to know calculus, and you don't need to know how we got from here to there. You just need to be able to memorize these bottom purple formulas for the zero, first, and second order. So now here we have these purple formulas that we arranged because of calculus. That's for the zero order, this is for the first order, and this is for the second order. And here is why we did that. If you look and see, these line up perfectly with the slope y-intercept format to graph, to put this stuff on a graph. So we have y here. Y would be the concentration of A at the end, your final concentration. And then this m, your slope, would be the negative k value, the rate constant. Your x would be the time. And then your b, your y-intercept, would be the concentration of A that you started with, the original concentration. That's why I put that O there. Your original concentration. And that's for zero order. Now for the first order, we have a different formula. We have this purple formula. The line, or natural log, as I was telling you about, you got to find that on your calculator and practice using it. The natural log of the concentration of your final concentration of A, that is all your y value. And then the slope is your negative k, and then your x value is the time, and then your y-intercept, very important, your y-intercept is the natural log of your original concentration of A. Now you're in your second order, the formula is slightly different, but it's still in the same format. You have 1 over your final concentration of A, and that's going to be y. And then your slope, your m, is going to be, look at this, we have a positive k in the second order. Because when it's a second order formula, it turns out that way. When you start doing the math and you start getting practice at doing this, you'll just notice that it starts turning out positive. Because the other ones, the zero order and first order, they usually turn out negative. So the slope is positive in this format, and that's the rate constant of k. Your x is your time, and your b, your y-intercept, is 1 over the concentration of the original concentration that you started out with for A. Now here's why that was important. Now you see how we have this this formula nicely rearranged in the slope-intercept form so we can graph it. So this is going to be your y-intercept. So your y-intercept is going to go on where the x is 0 and the y-axis right here. So whatever your original concentration of A was, you're going to plot it on the point at the 0x axis, but up on the y-axis right here. So that's your y-intercept. That's B. And then you're going to use the m, which is your negative k, is the slope. Or right here they have written k is the negative slope. It doesn't matter. You can say negative k is the slope, or you can say k is the negative slope. It's the same thing. And this is for zero order, by the way. And this is why we have to know if it's zero order, first order, or second order, because we have to know what formula to use in order to get a straight line like this. So you see how this line that we plotted with the points is a straight line? So this is the entire reason why we're using these purple formulas in the slope-intercept form, because when we plot it on a graph, it's going to give us a straight line, and it's a lot easier to compare. Now here's the first order graph, and this is going to be the natural log of the concentration of A, and the K is going to be your negative slope, or of course you could say negative K equals the slope. It doesn't matter, it means the same thing. And this is going to be a straight line because we used the correct first order formula. So if you're doing these problems and you plot them on a graph and it does one of these numbers, or it does something like that, it doesn't give you a straight line, then you've got the wrong order. You're doing it in first order and it should be zero order or second order or something, because all of these rearrangements of this purple formulas to plot it on the graph, the whole purpose of this formula is to get a straight line out of it. So if you're not getting a straight line out of it, if it's doing something like that, then you got the wrong order, and you need to go back and check and see what order this reaction is. Okay, and one more, the second order. Now the second order is special because if you notice, the slope is positive this time. The second order is the only time the slope is positive. So if you notice, K equals slope, this line is going up, not down. The other two, the slopes were pointing down. They were going from left to right down. But in the second order, the slope is positive, so the line goes up.